Hi everyone, today we are welcoming Héléna LADREYT, and she's a veterinary public health officer, and she's the epidemiologist for the Federal Initiative at Iran. And today she's going to present her PhD work about the modeling of potential human exposure to Japanese principal virus. So, thank you very much for me. So, hello everybody, thank you for inviting me. So as you said, I am pleased to present you a work on Japanese encephalitis that was part of my PhD, which is, this work is currently under review in TED. And it was founded by the French Ministry of Agriculture, ANSES, CIRAD, and Institut Pasteur du Cambodge. And it's about potential human exposure to GV in case of viral introduction into La Réunion island. And yes. So Japanese encephalitis is a vector-borne zoonosis, which is caused by a flavivirus from the same serocomplex than West Nile and Usutu viruses. It's the leading cause of human acute encephalitis in Asia, despite vaccination in half of the concerned countries. Despite advances in diagnosis and laboratory testing, the incidence is underestimated because of underreporting of cases and cross-reaction of tests. And 3/4 of the clinical cases concern children who develop more severe forms of the disease. And the vast majority, however, of the infection are asymptomatic, but the case fatality rate can reach 30%. And neurological sequelae are reported in 30 to 50% of survivors. GE affects all Southeast Asia, but one indigenous case was detected in Angola in 2016. And intrusions were reported in Northern Australia, but some months ago, GV emerged throughout Eastern and Southern Australia, with today 40 human cases and 5 deaths. According to the epidemiological cycle, the more traditionally described combine a wild cycle involving hard-eyed birds and a domestic cycle involving pig as the main amplifying host. The main vector known is Culex tritaeniorhynchus, but other Culex species are competent for GV, such as Culex quiquefasciatus. And non-competent hosts, meaning that they do not retransmit the virus to vectors, they include humans, horses, dogs, and cattle. Hard-eyed birds are considered the main reservoir, but studies are very scarce actually. And historically, pigs are central in GV epidemiology, but there is evidence to suggest that the cycle could be more complicated, like the fact that GE occurs in areas where there are few or even no pigs. And in this case, secondary reservoirs could be involved. For example, domestic birds have been shown to be exposed to GV in many parts of Asia and able in laboratory conditions to develop sufficient viremia to reinfect vectors that could feed on them. And in the first part of my PhD, we predicted by modeling a possible circulation of the virus in system with no pigs. Moreover, Culex are often opportunistic vectors, so it means that they can feed depending on availability on pigs, poultry, dogs, cattle, and humans, which is why all the hosts, both competent and non-competent, on which the vector can feed, should be taken into consideration to study the transmission dynamics of the virus in order to identify potential dilution effects. So anthropogenic landscape changes as habitat destruction, fragmentation, encroachment on wilderness areas and global warming, they contribute to the expansion of mosquito vectors and the emergence of arboviruses. Human exchanges and trade also shape the distribution and intensity of arbovirus transmission by impacting vector and host distribution. And they already have led to the emergence of arboviruses in new regions, such as West Nile fever in the US and Zika in Brazil, for example. Réunion Island is located in the Indian Ocean, 700 kilometers east from Madagascar. And some vector-borne diseases have already been introduced in Réunion Island, and have caused or are causing serious public health problems like chikungunya, probably introduced from East Africa via the Comoros Islands, which caused an epidemic affecting nearly 40% of the population in 2005-2006, and dengue, which seems to have become endemic in Réunion Islands since 2018. Vector-borne zoonoses this time have recently emerged in Réunion Islands, such as flea-borne murine typhus, or are under special surveillance because they circulate in the region, such as Rift Valley fever, which circulates in Madagascar and in Mayotte, and West Nile fever, which circulates in Madagascar, and for which antibodies have been detected in horses in Réunion Island, with no observed indigenous human cases yet. In the Indian Ocean, trade is important and growing, so numerous commercial cargo lines exist between Réunion Island and GV endemic regions, such as Southeast Asia, which ensure the importation of goods in 18 to 30 days, which may be consistent with the survival of infected Culex species, adult Culex species on board, which live on average 25 days. Also, among the 12 species of mosquitoes known on the island, the potential GEV vectors Culex quiquefasciatus is present and abundant, as well as Culex tritaeniorhynchus. The competent hosts, pigs and poultry, are bred on the island, and the accessible and habitable territory in La Réunion Island being restricted due to the landscape. It's an ancient volcano. Farms are concentrated in a coastal and intermediate area corresponding to the area where human population and mosquito densities are the highest. So because of commercial links with Southeast Asia, the presence of potential GV vector in La Réunion Island, competent hosts also being present in Réunion Island, as well as the fact that GV mainly circulates in tropical climates area, which is the case of Réunion coastline area, GV could be introduced in Réunion Island and spread. So the objective of this study was to analyze the ability of epidemiological units composed of pigs, poultry, cattle, dogs, humans, and vectors in Réunion Island, to allow GV to invade these units in the event of an introduction of the virus, and to estimate the size of the human population that would be exposed should it occur. So we considered all these hosts, both competent and non-competent, as we saw that as GV vectors were opportunistic, we need to consider the whole system to analyze the transmission dynamics of the virus. So to achieve this goal, we used an existing deterministic dynamic transmission model that incorporated pigs and poultry as competent hosts, and cattle, humans, and dogs as non-competent hosts, as well as mosquitoes of the genus Culex species, as potential vectors of GV. This model that was already published allowed reproducing serological field data in Cambodia, which is a disease endemic region. The basic reproduction number, as you know, is the expected number of secondary cases generated by a primary case in an entirely susceptible population. And it's the indicator commonly used to measure whether or not a pathogen can invade a population. So we use this model to estimate R0 or R0 in the epidemiological units that we define. And we calculated the size of the human population living in the units where this estimated R0 was greater than 1. And so that would be potentially exposed to GV. First, if the virus was introduced in one single epidemiological unit, and second, if it had spread all over the island, worst case scenario. So the larvae of the most abundant Culex species mosquito in Réunion Island, Culex quiquefasciatus, pullulates in all urban water rich in organic matter or polluted by detergents, as well as in rural area in polluted water of agri-food discharges, and for example, domestic water supplies or manure pits in farms. So we therefore considered that each identified pig farm in Réunion Island had at least one mosquito breeding site, namely the manure pit, which was therefore predicted throughout the year. In the island, the 256 pig farms that we identified are mostly family-run, small size, and open, they breed the pigs in open buildings. And poultry is also raised in open buildings or in backyards. So also regarding the non-competent host, in addition to humans, cattle is raised in extensive outdoors farms, and domestic but also stray dogs are numerous and also live outdoors. So the model epidemiological units were then composed of the pig farm, the associated Culex species population that is bred in the manure pit, and competent, so pigs from other farms and poultry, and non-competent, so human, cattle, and dogs, hosts, that live within Culex average flying distance, which is 1 kilometer. So we obtained the sizes and locations of pig, poultry, and cattle farms, as well as human and dog density from different sources. And here are the 256 pig farms that represent the 256 units, epidemiological units. The model was a deterministic compartmental SERR model, susceptible, exposed, infectious, recovered model, which operates in continuous time and which was initially developed to simulate the transmission of GV between Culex and competent hosts and from Culex to non-competent hosts in rural multi-host system in Cambodia. This model allows the estimation of R node of the epidemiological unit. In each unit, the population size of each host species, so swine, chicken, ducks, cattle, dogs, and humans, were calculated by intersecting a 1 kilometer radius buffer zone drawn around the pig farm with GIS layers of either farm location and size for production animal, either population density for human and dogs. This allows us to create this kind of map with the different density of hosts in each epidemiological system. Réunion Island pig farms were generally located at similar low and medium elevation, and because of the small size of the island, we assume that environmental and climatic conditions that might affect vector abundance varied only slightly from farm to farm. So for this reason, and since Culex species larval sites were supposed to be related to the farming activities, so the manure pits, we assume that at a given date, the size of the vector population did not vary between epidemiological units. The available entomological data did not allow us to determine the real vector population size in the epidemiological units, because it's something we cannot observe directly on the field. In the Cambodian model, its size had been estimated with calibration and estimation based on serological data. And it was estimated to be around 50,000 vectors per unit of this same size of the one we have in Réunion Island. Here, we use arbitrary values from 100 to 100,000 vectors per unit to explore actually the values that would take R0 according to different seasonal and other environmental conditions that would influence vector population dynamic. Indeed, this model runs in each epidemiological unit and estimates R0 for vector population, ranging from 100 to 100,000 vectors instead of 1,000 vectors. So we calculate two indicators for the size of the human population, potentially exposed, So which means that it's the population living in a unit where R0 is higher than 1. And we plotted this indicator against the vector population size. So first, in the case that GEV would be introduced in one single random epidemiological unit, for this indicator, we used a network approach to represent situations where GEV could spread between adjacent units where R0 would be higher than 1. So we filtered the units where R0 was higher than 1 for each vector population site. We did that. And we computed the adjacency matrix between these units based on the intersection between the 1 kilometer radius buffer. Then for each of the 256 units, if R0 was higher than 1, the size of the exposed population was the number of people living in the geographical area formed by the spatial union of these units and the neighbor units where the R0 was higher than 1. Could come back on this later. And we thus obtained 256 values of potentially exposed population size that form the distribution from which we extracted the median and the 2.5 and 97.5 percentiles. In a second step, in the extreme case where the virus would have spread all over the island, we plotted just the sum of the inhabitants that live in units with R0 higher than 1 against the size of the vector population size. So as a result, here I can present you the location of epidemiological units with R0 higher than 1, higher or equal to 1 for each size, for 6 sizes of the vector population. So if introduced, GEV could invade more than 75% of the units if the vector population size by unit were similar to the one estimated by the model in Cambodia, around 50,000 vector per unit. And also 2 epidemiological units in the south of the island had an R0 higher than 1 with only 1,000 vector in the units, which is a 1 kilometer radius buffer zone. An epidemiological unit located in the neighborhood of the port area in the northwest of Réunion, which is a potential gateway for GEV, had an R0 higher than 1 with only 10,000 vectors and more, from 10,000 vectors. Similarly, several units where R0 was higher than 1 with 10,000 vectors and more were located near the regional airport of Saint-Pierre in the southwest of the island. For the human population size potentially exposed to GEV, so this first plot represents the size of the human population potentially exposed if GEV was introduced in one single unit and would circulate there in this unit as well as in the adjacent units where R0 is higher than 1. So the plain line is the median and the 2 dotted lines are the percentile. And the vertical green line represent the vector population size estimated by the model in Cambodia for a unit of a similar size. So the median increased from 25,000 vector per unit and would cape at around 3,000 potentially exposed people. The 97.5% percentile of this distribution here would, however, would reach around 16 to 17,000 people with about 50,000 vector per unit, which represents a little less than 2% of the Réunion population. The second indicator represented the maximum exposed population size in a situation where GEV would have spread all over the island and would circulate in all the epidemiological units where R0 is higher than 1. The blue line corresponds to the whole population and the red lines focus on just young people because the assumption was that young people, something that we know, that young people are more prone to serious forms of the disease, so we wanted to focus on them. So in that case, nearly 80,000 people would be potentially exposed to GEV if there were 25,000 vectors in one unit. And if the vector population size exceeded about 60,000 vectors per unit, we would have up to about 20% of the Réunionnais population, which means around 180,000 people that would live in epidemiological units where the estimated R0 was higher than 1. So we ran a dynamic model in different epidemiological units identified in Réunion Island to estimate R0 and the size of the potentially exposed human population in case of GEV introduction. The host population sizes were fixed based on field data. And as vector population size is not something that we can directly observe on the field, and as it varies with the season, we systematically explored arbitrary vector population sizes by unit, per unit. So we saw that GV may be able to invade part of the epidemiological units, as we had units where our node estimated was higher than 1. One epidemiological unit at risk, so with an estimated R naught higher than 1, with 10,000 vector per unit, was located within a few kilometers of the island's ports, the big ports area, the region of Le Port, which connects Réunion to GV endemic regions, and that represents a significant risk of GV circulation in this unit if infected vectors were introduced by cargo. So beside the risk of introduction and local circulation, we have also the risk of diffusion with, for example, the importation of containers. And almost 20% of the units could be invaded with, for example, 10,000 vectors per unit. So for comparison purposes only, and all parameters and conditions considered equal, which is quite important, more than 75% of the units would have R0 higher than 1, and about 150,000 people would be potentially exposed if the virus was everywhere on the island, with a vector population size being the same as the one estimated in Cambodia, around 50,000 vectors per unit. So just as a comparison. So beyond the size of the population, the zoonotic transmission depends on trophic behavior, availability of hosts, and the capacity of the virus to replicate in them. So these parameters, the problem is that they vary from region to region within the same species. The vector competence parameters we used in the model came from studies made in different regions. So it is needed to evaluate local parameters as the competence of local Culex tritaeniorhynchus, Culex quiquefasciatus for GEV. But also it could be interesting to evaluate the competence of local Aedes albopictus for GEV, which has been shown to be potentially vectors for GEV in the lab. Also the host feeding preference, so the fact that a vector prefers this or this host to have this blood meal. These parameters values came from a study led in Cambodia. So in the same way, we should evaluate these parameters for local species. And more data would be also needed to confirm or not the big simplifying assumption of using only one Culex species vector population, and we did not differentiate the different potential vector species like Culex quiquefasciatus, tritaeniorhynchus, and maybe even Culex neavei, which is present in Réunion. Then environmental and climatic conditions are highly variable over very short distances in Réunion Island. And for Aedes albopictus, this leads to strong variations of the spatial distribution of breeding sites of Aedes albopictus. But this is not the case for Culex quiquefasciatus because it is really linked to manure pits and agriculture activities. However, the size of the farm and so the size of the manure pit could influence Culex quiquefasciatus abundance between farms. And again, more field data are needed to confirm or infirm the assumption we made on this point. So if GEV was introduced in one unit, we saw that the size of the human population potentially exposed was relatively small. We had a maximum of 3,000 people. And so it shows that the presence of GEV might not be detected as the proportion of clinical cases once you're infected is very low. And GEV is not part of the differential diagnosis for human or animal encephalitis. So once introduced, in addition to the risk of local circulation in the unit of introduction because of batch management of pigs and the continuous renewal of susceptible competent hosts, and also because of the presence of vector all year long, GV could spread, more or less before it is detected, because the number of people potentially exposed would be relatively small at the beginning, so we would not detect it. So again, in the worst case scenario, up to 20% of the Réunion population could be exposed if the virus had spread all over the island. And this probable delay between GV introduction and its detection justify the need to implement surveillance. For example, we could and we should include GV infection in the differential diagnosis of human encephalitis. We could set surveillance of reproduction failure and mortality in pigs, because it's one of the impact on animal health of GV. And the surveillance of reproduction failure and mortality in pig farms, this is how GV emergence was detected in Australia this year. We could also raise awareness of vets and farmers and put in place passive entomological surveillance system at the potential entry points with, for example, FDA cards. Also routine serological monitoring in pigs at the slaughterhouse to detect possible emergence, and the reinforcement of communication on protection against mosquito bites, which is already done for dengue infection in Réunion Island. And that's it. I'm sorry if I was a bit long. So thank you very much for your attention, and thank you a lot to everybody that actively participated to this project, and my supervisors, Benoît Jorin, Véronique Chevalier, and the whole team. Don't hesitate to ask questions. I'm here. Thank you. Je partage, non, c'est bon. Alors, j'ai une première question. Yeah, we can talk either in French or English. Alors, je lis la question de Karen Maikop, merci beaucoup. Are there any natural bird hosts on Réunion Island? If yes, how might this change the diffusion and exposure rate to GV? Could this not also be a possible way of entry to the region? So yes, as I said in the first part, studies on natural birds host and being the main reservoirs of Japanese encephalitis are actually very scarce. And sometimes they are scarce, and there is a circulation of GV in regions, for example, in Cambodia, where the number and the density of wild birds, and especially hard-eyed birds, are very low. So that's why we questioned, and we are not the first one to do that, but we questioned this epidemiological cycle. And in Réunion Island, there are some natural bird hosts, but in this particular system, we just focused on this very actually closed epidemiological system because of the distance of circulation, of flying distance of mosquitoes, and because of the fact that in the region we observed, the density of wild birds was very low. So we didn't explore this, but I think if we made a more complete and more widespread model, it's very important to include wild compartments. Although the studies on their competence and the fact that they would be reservoir are very scarce, unfortunately. But I would be very interested if you have information on this.
Vous m'entendez?
Oui.
Hi, Héléna. Thank you very much for your great talk. You mentioned very interestingly on your last slide that we have a low surveillance capacity around the world for this disease. And I was wondering, given the current situation of avian influenza, where we can see wild birds moving avian influenza across continents, and in South America, we're seeing it coming from the US, who already saw it coming from Europe. Do you think that the American continent should also be worried about this? Because we have seen very similarities with introduction of West Nile that went from, is going from north to south. We have Culex all across the continent. So based on your works and your modeling in La Réunion, do you think that it's just a matter of time for Japanese encephalitis to arrive to the Americas? Thank you.
Thank you, Julio. Yeah, it's a complicated question. It's hard to, but yes, as we, with the example of Australia, actually, and the indigenous case found in Angola, I think the risk exists everywhere. But the thing is that, again, with a wild bird, we don't know how wild birds are host and reservoir for GV. It's not the same than for West Nile virus. And for Réunion Island, for example, we identify the biggest risk as the introduction of adult infected mosquitoes being transported by cargoes, because there are these lines that there are the cargoes that transport goods in less than 25 days from Southeast Asia, where the prevalence is really important, and Réunion Island. It would be also the case, I mean, for me, it would be a risk for also South Africa, because these cargoes also go in South Africa. And in 25 days is still okay to let Culex infected adult mosquito live. So I think it would be interesting. So we could just actually test the model with some epidemiological system. If you say that all the conditions might be gathered to allow for GV to invade some epidemiological system. And I think there is also a big effort to do on the risk of introduction on cargoes from, I have to see if how long the cargoes come from Europe or maybe another regions to Southern America, or even from Australia. Maybe that would be interesting. But we don't have to forget the transport by air, which can also lead to the introduction of infected vectors. So it's a good question. As you see with my answer, I'm not super sure of what to answer, but I think it would be interesting at least to test the model in a specific epidemiological system in Southern America. For just on the first step, would see, would it circulate, would it invade this epidemiological system? I think it would, unfortunately. I'm sorry for my answer, it's not very clear.
No, thank you, Héléna. And you actually raised a very good point, because the South America has a Pacific fair trade is not the word, a direct trade with Asia. And we actually get cargoes directly from China, and there's a specific treaty between South America and Southeast Asia that we probably actually get imports from China and other countries in less than a week sometimes, or 2 weeks. So if you are, the times that probably take to bring the infected mosquitoes will be very much in line with the times that you are suggesting. So thank you for that. It's worthwhile to look at that trade.
Okay, yeah. Thank you for your question.
I have a question. Just about C'est juste pour la taille de la population de vecteurs. Est-ce que tu as eu des données de terrain de capture à la Réunion?
Alors, donc là, should I answer in French or?
I can repeat my question in English, just about the types of the vector population, if there are some field data.
Yes, so that's also, so this, how I present you the work is, we did change this approach because at first the plan was to have a, so much to speak in French, to have a field data over 1 year of mosquito traps, which you can see here on the picture. The idea was to trap mosquitoes over a whole year in Réunion Island to estimate abundance and most especially the dynamic of the abundance of mosquito species. So we had data. So I went there and we went with the team, Marlene and Nausicaa, to capture, to trap mosquitoes for a whole year. So we have data. The problem is that the first idea was to have comparable data, capture data between Cambodia and Réunion Island. And in Cambodia, they trapped in the area where we studied and for which we developed the model, they trapped mosquitoes without CO2 in their traps. And so we set mosquito traps without CO2 in Réunion Island, which led to very few captures, very few mosquito traps in Réunion Island. Like I had for over a year, I can show you later the numbers, but like 700 or 800 mosquitoes trapped over, I mean, Culex or aiguës trapped over 1 year, while in comparison in Cambodia, it was like 10,000 for one night. So the idea to have these two comparable abundance data would be to create a ratio between these two captured data, because in the Cambodian model, we calibrated the model on serological data, like blood sample collected on pigs and poultry. We calibrated the model, and which allowed us to estimate a vector population size, which was this 50,000 vector population size per unit. So the model estimated this number. And the idea was to, this is something that we did first, was to create this ratio of how many vectors we captured in Réunion Island and how many we captured in Cambodia, create a ratio and apply it to this vector population size we estimated in Cambodia to have an estimated vector population size for Réunion Island. I don't know if it was clear. The problem was that we had very few captured mosquitoes, trapped mosquitoes in Réunion Island. So this ratio had was very not robust. I don't know how to say that. And so it was a bit complicated to go along with this ratio. And we literally changed the way of thinking the problem by using this completely arbitrary vector population size. And also this helps, this allows us to see different scenarios, like if you're in winter and the vector population size are very low, we would have that many epidemiological units which are not higher than one, and so that's why we changed the thing. But other than trapping, how to say, marking, release, recaptures, it's very hard to estimate the vector population size in an area. So without this field data, we cannot do more actually. Was it clear? Yes. En français, je crois. Dans le chat aussi. Bon, j'espère que je ne vous ai pas trop perdu à la fin.
Thank you, everyone, and thank you to Héléna. And see you next week for the next seminar with Héléna. Okay. Thank you.